This is Rosen, Discrete Mathematics and its Application. We're in section 9.3 on primes and greatest common divisors. Here we discuss the very important Euclidean algorithm. And the Euclidean algorithm is an application of the division algorithm by which we can find a greatest common divisor of two integers. Here we have two integers. We say that the greatest common divisor of A and B is equal to the greatest common divisor of B and C when A is greater than C and C is the remainder of A when divided by B. Well, we know how to do that. We use the division algorithm to find the remainder. Let's take a look at an example and then we'll prove the result. So we want to find the greatest common divisor of 91 and 287. We set up the division algorithm and we get 287 is a dividend, 91 is a divisor, times 3 plus 14 is the remainder. And we are stating that 287 and 91 have the same greatest common divisor as 91 and 14. What we're going to do then is find another pair that have a greatest common divisor by making 91 the dividend, 14 the divisor, finding a new remainder of 7. So 91 and 14 have a greatest common divisor. It's the same as the greatest common divisor of 14 and 7. 14 becomes a new dividend, 7 becomes a new divisor, and I get 14 is equal to 7 times 2 plus 0. Of course, 14 and 7 have the greatest common divisor of 7. And that whenever we get to a 0 remainder, that is a stopping condition. So the greatest common divisor of 287 and 91 equals greatest common divisor of 91 and 14 equals greatest common divisor of 14 and 7, which is 7. All right, why does this work? Let's take a look at this lemma. If we have integers a, b, q, and r that we associate with this division algorithm, where a is a divisor, b is a dividend, r is the remainder, we say that greatest common divisor of a and b is greatest common divisor of b and r. How do we know? Well, first let's suppose that D divides both A and B, and there must be something that divides it, even if it's as small as 1. Then if we subtract BQ from both sides, we get A is divisible by D, B times Q is divisible by D, therefore R is divisible by D. So any common divisor of A and B must be a common divisor of B and R. Okay, but similarly, let's suppose that D divides B and R. But then since D divides B times Q and D divides R, D must also divide A by that same theorem. So any common divisor of B and R must be a common divisor of A and B. And therefore, the maximum of those common divisors must also be the same. Therefore, the greatest common divisor of A and B is the greatest common divisor of B and R. Let's look how this works in multiple applications of the division algorithm and the Euclidean algorithm. If I set up my two integers such that a is the larger one and b is the smaller one, I've got a is equal to r naught, b is equal to r1. Remember that the first remainder, r2, will be strictly less than r1. And the next remainder, r3, will be strictly less than r2, so that eventually it has to get down to 0. So repeated applications of the division algorithm with the divisor becoming the dividend, the remainder becoming the divisor, must come to an end. And it can't, since R1 is equal to B, it can't take more than B plus 1 applications of the division algorithm. And by that prior theorem, Each one of those pairs has greatest common divisor. And when we get to our stopping condition, the last non-zero divisor will be that greatest common divisor. And that's what we say here. And that is how the Euclidean algorithm works.